So this morning, somebody asked me after the speakers' dinner, one of the speakers asked me, because we clearly had good fun like now, how long do we know each other? So I think for me, GeeCON is like Christmas, but better. It's like all people I love, but I don't have to cook anything. Ideal. Okay, so final talk for today, or the only lightning talks later. We'll talk about distributed systems, and without mentioning any particular technology or any particular database or anything, but we'll just focus on Java primitives and how we can build it step by step. Tomer yesterday had a very nice talk about how database works, but he focused on B trees and LSM trees and how these things help you to store data efficiently. But there's a premise that he kind of mentioned briefly, that it applies from the moment that the system has confirmed it has the data. So you got the write. Write was successful, and now you try to store it. What I'll be covering today is the premise. So what happened, or rather what can possibly go wrong until you get this acknowledgement that I've written the data successfully. And that will be covering today. As all of the GeeCON talks, there is a Slido, which I'll open at the end of the talk, where you can do the questions. And obviously a disclaimer. This talk is not intended for anybody to go and implement a distributed systems. I will never do it on my own, even though I've been in a couple of projects that were trying to build it or were trying to use it. This is more to understand what's under the hood, like level -1 of your architecture and how things operate in the distributed systems. Very briefly, because we have less than an hour, but I hope in a good enough manner so that you can go and explore whatever is interesting to you. So we'll be talking about distributed systems. So a collection of distinct processes which are spatially separated and which communicate with one another by exchanging messages. This is from a paper from Lately Nineport from nearly 50 years ago. I hope I'll be able to be at GeeCON in 3 years, and we'll probably get another talk about distributed computing, quoting 50 years old paper. Pretty awesome. In other words, we will be talking about system in which failure of one of the computers we didn't know even existed can render our own computer unusable. The same guy, just a couple of years later. So we'll have a situation where we have a couple of nodes, machines, Docker, containers, call name as you want it, that somehow talks to each other. And what we'll briefly do, we'll try to get to the one node with some data, saying, hi, I'm Jakub. And we'll get a session key, which we'll use to get the other node so that we can get a response back. And we clearly see that this system is supposed to remember the state between the operations. So we are talking pretty much about very simple session replication among multiple nodes and how we can build it and what we need to build it and how we can do it step by step and what Java classes, elements can help us achieving that. So what we'll need. We'll need to listen at port 8080. We'll probably need a concurrent hash map, some magic, some sharks, and then we are done. That's not that easy. We'll need a clearly HTTP server, something that listens to HTTP, or build something that listens to HTTP traffic, and then build a distributed store, something that the data we've stored distribute among all the members. And this distribution is pretty tricky because we have to manage the incoming and outgoing traffic. Because we have a single node, something gets in, something gets out. We have to understand who can we talk to. So we have to discover the members somehow. We have to somehow get the information what we need. We need to set up a cluster, a couple of decisions to make. Then we have to distribute the data. We have to serialize this data because we have objects, and over the wire we have bytes. So we have to serialize this object. And then, finally, we have to decide how we control concurrency, because there will be concurrency issues, for sure. So if you're ready, I'm John in Knoxville. Welcome to Jakub. We'll start with HTTP server. Java has some HTTP support already, which is kind of rudimental, but for our case, it's good enough. And to be honest, I even a couple of times recently used it on production systems. So we have the HTTP client in JDK 9. As a preview, I think it's from JDK 11, so a couple of years already. And we have HTTP server in Java. Some people get ballistic when they see com.sun whatever package. It's fine. It will be there. As long as it's not deprecated, it will stay in our JDK. So it's kind of safe to use it. Though the HTTP server is pretty basic, and unless you have a very simple examples, like you just want to send a flat file, and that's all you need. That's good enough. In both cases, this is kind of a basic. So, for example, HTTP client, if you think of using it in your project, you can't intercept the call. There's no easy way to make it interceptable. There are already some libraries that can help you with that, or you can look up Micrometer, who is doing observability around the HTTP client, has done it somehow. Like, URLs do not expand in the way you have in all other HTTP clients. So again, very basic, but included in the standard library, which is helpful. HTTP server feels like a very young brother of serverless API. But yeah, we can use it. So we have a HTTP server. We have to define where we are listening to, and then we define a handler, in that case healthcare, say exchange, send response, and that's we are done. This is the whole HTTP server in Java in a couple of lines of code, and it's working. Funny enough, I used it recently. I used that approach in one of the recent projects where we had a process which didn't have an HTTP server, but what we had to do is to expose some Git details of a version. That was good enough. What happened? Oh. Okay. Now we'll have to fix. Oh, I see the difference. Now I can hear myself. The other thing is the client, and that looks pretty standard. We fire a request, we have a builder, we can do some additional headers, and that's pretty much it. And that's within your JVM, so no additional libraries. It's a good start. Things ain't that easy if we get to actual distribution of the data. So building up the distributed store. So first of all, we have this concept of multiple nodes. Let's call it node 1, 2, 3, whatever. We would like to form a cluster, and each of the node will listen on HTTP port, which we already covered, and will listen on some socket, which will be for internal messaging within the cluster. We have HTTP, so now let's do the socket connections. Again, very simple. We just use the old sockets. Not that because it's extremely helpful. There are better ways to do it, but kind of drilling down into Java, new I/O, and all the channels will probably exceed this talk. What we need a simple communication. But there is one trick here, this magic of deserialization. Whatever we put into the socket, it goes over the wire, and we need a byte representation of whatever we are sending. And we will cover it in a second. But first of all, we need to understand where we are sending data. So we need to do a kind of a discovery. What we can try to do is we can define a static list of nodes. So I know I am setting up 3 instances. Each instance has a different IP address, different port, whatever. I can define this static list. And unless we are using a fixed data center, that doesn't really make sense anywhere, unless testing. But starting point. Then we can do any kind of, let's say, deployment context-aware discovery. So if we are going Kubernetes, there is an endpoint that we can reach out to, and it can tell us, hey, your service has this number of instances, of pods, and these are IP addresses. Just take them. So we can have dynamic discovery, but it's outside of our application. Same goes with AWS. If you are deploying as ECS, you can have AWS API, SDK, to reach out to get that information. Nothing interesting. But what can we do is we can build it on our own based on multicast discovery. And that's what quite a lot of distributed systems do, in fact, in some cases, so we can handle it on our own. So for those who don't know, multicast, like whenever we think now about making a connection to anything, we usually, because we are lazy, think about HTTP. HTTP is a TCP, so transmission control protocol. There is a connection, both sides agree to a connection. But networking has a lower level, a datagram level, so UDP. We can just broadcast to everybody, hey, I'm here, hey, I'm available. And that's pretty much what we'll be doing. We'll just broadcast to everybody, and whoever wants to join will join our cluster. That's, for example, how the default behavior of Hazelcast is doing. So what do we have? We need some type of data structure that will contain our local IP address and port. I'm also using cluster name just to be able to distinguish logically different clusters. Unless we want everything in the same, all nodes in the same cluster, that's not needed. And then we create a multicast socket where we start sending data. The multicast sockets is a kind of a subset of our IP version 4 address space, where we can form a group, and then whatever we send out to this group, whoever joined that group will receive it. There's no order, there's no guarantee on receiving that. That's why most of the systems just do it continually for a period of time, but we're just broadcasting that we are available. If you're having any type of home sensors at home, they usually start communicating with each other in a similar fashion. And then, when we have this member info, we just push it over to as a datagram to the socket. And then multiple other numbers, multiple other nodes that are active, that has joined the socket, can receive it and say, oh, there is another IP address that we can join and collaborate with. So we get a couple of nodes that know a little bit about each other. And we have to decide how we would like to set them up to talk with each other. So we can have 3 nodes. If we have more, there will be more of a star topology. But we can have a star topology where we have one or more centralized nodes which orchestrate exchange of messages between different nodes. But that's not the only topology. That's not the only way we can formulate the cluster. We can do a circular topology. So we can say node 1 is talking with 2, node 2 is talking with 3, and then we circle back to the node 1. And we can, just because we are lazy, just say everybody is talking with everybody. Now we can say, hey, that's extremely chatty. That's, a lot of traffic. Yes, it is, but there are some data stores that are actually using that way. That gives us one advantage, because if I say we are using star topology, I have to decide which of the nodes is the main node, which is the master, which is the leader, and then how to pick up the followers. There are a number of so-called quorum or consensus protocols, which I don't want to cover. There was a really nice talk yesterday from Andrew from Hazelcast, where he was talking about some of the problems Hazelcast was having with their Raft implementation and how to elect a leader. I don't want to do that. I'll just assume that this is a leaderless cluster, which is possible. That will hit me in the future, but we'll get there. So as I have a cluster, so I have a number of machines that know about the existence of other services. The next thing I have to decide is how to distribute data. So there was an update, or there was a change in state in one of the machines, and I want that data to be replicated to all the others. So first thing is I need to queue the changes. I need to have a certain way to distribute my workload. So I can have a Java blocking queue, which in my case is an inbox and an outbox, so incoming data and outgoing data. And then I have two infinite loops, which one is pulling out of the outbox and sending it out to the other member. In that way, already in a point-to-point fashion, in an unicast way, not with the datagrams, though I can do it still with datagrams, but it won't be as efficient and as stable. And then, on the other hand, I am listening to the number of queue, to inbox queue, and whatever handlers I've registered for different operations within my cluster, I can process the data in a way I want. As you can see, it's a continuous loop, so not to block, I'll just put it in the either a set of virtual threads, as I'm that fancy, or just a set of executor pools that will handle that independently and not blocking the main thread. But sending byte over stream, over TCP is easy. Devil is in getting those bytes. And that's what we'll cover as the next. So serialization. Again, you can say, hey, Java has a serialization. Why can't we use it? Well, we kind of can. Because Java serialization turns our object graph into a stream of bytes, and that's exactly what we want. Though it has some deficiencies, and if you drill down a little bit further, it's like they say, oh, it's bulky, it is very CPU heavy. Worst of all, well, the worst is that it really requires me to keep the format of my objects, because the changes of the object can impact the serialization. Sometimes a change in the class can make my all object unserializable. And worst of all, this is very Java specific. So if you want to go to any other language, that's close to impossible. And this is not only me who is seeing that. Obviously, Java guys also see that. Joshua Block in his Effective Java just wrote that he sees no reason for using Java serialization anymore in any project. I don't know why he's mentioning protobufs, maybe because he's working at Google, but he's also mentioning JSON, which is funny. So we have other ways. Most of the distributed system vendors are giving us some other ways to serialize data. Protobufs is one of the examples. Kafka is having its own way. Hazelcast is having its own way. So different companies, different people are trying to find a way to correctly serialize data under some restriction. And so is doing Java itself. So Brian Getz couple of years ago, wrote an article towards better serialization. I can't remember whether it was related anyhow to the whole bike shedding of optionals not being serializable, but there is a plan for Java to evolve. What he wrote is that we can make serialization considerably simpler and safer by narrowing the goals explicitly to reflect this reality. We should seek to support deserialization of data, not objects. And if you've been to a talk yesterday about, if I recall correctly, data-oriented programming, that's a part of this effort. So what we want in our serialization effort is to extract the state of the object, just the data. For example, be able to do it based on a schema and store or work with this schema independently of the data. That's what protobufs are doing. They let you have a schema, define what's inside the object, and they use this schema to serialize and deserialize data. We need to decide on the form of serialization, how we want to do it. In our case, it was byte array, but it can be something different. And then we have to decide, do we really want to version? And protobufs don't really version by default. Do we envision a schema evolution? Will we change the schema? Will it be append-only schema? Will it be remove objects or add objects, changing types of the fields, and so on? If you've ever seen a protobufs, real-life protobuf project, it has all deprecated fields throughout its history. Then we have object reconstruction. So when we send data over wire, do we always want to deserialize the whole object graph? Or do we want to deserialize just a subset of it? Do we know that there is a field and all we want is just the value for this particular field, not the whole objects? There's a couple of things that we can't forget when doing any way of a serialized object and sending it over the wire. So even though Java has all those things, they come with a couple of glitches, as you can see. But let's assume we've picked up the form of serialization. I can't tell you which is the best one because I don't know what you're trying to do in your distributed system. But for the sake of any presentation or an example, we can just use Java serialization. As long as we change all the members together, and that's what you usually do in our pet projects, it's good enough. But the moment we know what we want to send and how we want to send it, we get to a very difficult problem of controlling the concurrency between my members. So I can have a situation where I have a cluster and everybody is talking with everybody. And I want to do two operations. I want to do a put operation which has the same value or reflects or addresses the same key on two different nodes. And somehow, I want these nodes to converge, to get to the right value and figure out how they should, what value should be the final one. And when we have values stored across multiple servers, we need a way to figure out what was stored first, what was stored the second, and that way know what wins. And funny enough, it is 25 minutes of the talk, and I haven't yet mentioned CAP theorem in a talk about distributing computing, and this is a time to talk about a little bit about CAP theorem and causality and ordering. So, we have a certain consistency guarantees in any type of a system. We can have strong consistency. We can have eventual consistency, and something that some people refer to as accidental consistency, which I'd rather refer as permanent inconsistency. And these are states of a system you can observe in your real life. And we obviously don't want the last one. But before we get it, the strong consistency is when we have a couple of clients interoperating with the system, and at some point, one of the clients updates the key, and other clients keep reading. So as you can see, the client number one, the first swim line, has read a new value, a getter token that was equal to 2. And strong consistency means that from that moment, all other clients will get version 2 or later update. There's no way any of the clients will get an old version. That's what strong consistency means. Can we get it in our system? Is it possible to design our distributed system in a way that we can achieve strong consistency? That's where CAP theorem kicks in. So we had this all-to-all topology, and CAP theorem tells us that, in its essence, that you can have that your system. There are 3 attributes of your system: consistency, availability, and partition tolerance, which means consecutive reads will get you the same data. That's consistency. Consecutive reads will always get you some data. That's availability. And the reads will get you data whatever is the state of the system. So as we can talk to each and every member individually, we kind of take partition tolerance for granted. And, well, partition tolerance for granted and availability for granted, because if one member is failing, we just can talk to other member. So the system is available all the time. We haven't done anything to forbid this operation, so we cannot do anything with the consistency. So strong consistency in that case, in that topology, is not for us. If I've made a different decision earlier on, and that was a leader-follower kind of topology, I had a certain partition owner or certain key owner that I'll always hit the same member to change a value, then I can do it differently. Then I can do a stronger consistency guarantees, because if that member is not available for whatever reason, I can inform the client, hey, I cannot perform the update. So I don't have availability, but I have stronger consistency. In my case, any node can perform an update, and the client will not even care if the update has been distributed correctly. So strong consistency is not for us. And we obviously don't want permanent inconsistency. So we don't want a situation of losing data. We don't want a situation where there was an update on one of the members, one of the clients did an update, and this update was not propagated, and the client didn't even know about it. So we don't want a situation that the first swim line hasn't reached the update and just keep on getting the old data. That gets us to an inconsistent state, and we don't want to do that. So what we want to focus on is this reddish box, where we have a number of operations queue on each of the members on the nodes, and the operation is propagated to the additional members or to all other members. And those members see that there are concurrent updates coming, or well, at least they should see. So getting back to swim line is pretty much this one. So I have update to 8, update to 2, and what should the middle swim line decide? Is it 2 or is it 8? Again, Leslie Lamport, in distributed systems, it's sometimes impossible to say that one of 2 events occurred first. We have found that problem often arises because people are not fully aware of this fact and its implications. So can we figure out which was coming first? There are two other concepts that we have to tackle a little bit. So it's global ordering and conflict-free replicated data types. So can we decide on a causality in the distributed system? Can we decide which change we should apply? What was first, what was second, and what is the implication? Once we can order the events or changes on the or any other operations, we can apply them in a safe way. And one of the ways people are thinking about that is, hey, I can use timestamps. Clocks is a pretty good way to synchronize, at least between human beings. Why can't I use my computer clock to do any kind of order? And before you ask, using timestamps for concurrency control in a distributed system, as soon as you get outside of a single machine, is just a bad idea. It's a bad idea for at least two reasons. One thing is the time that you're getting in your computer is coming for a quartz clock, and by design, by physics, this drifts, this jitters. If you're having an enterprise-grade server, you might not notice that, but if you see any edge computing, smaller device, which, for example, gets hot and gets a lot of processing, the drift of the clock can be significant. And the other thing is, in Java, we have this method called system current time in milliseconds. And this is a not monotonic value. This is a wall clock. This is a clock of our computer that's synchronized with NTP servers and gives us a wall time. So this clock can travel backwards. We can have multiple reads and get the same value, or even get an older value. There is another method in Java, which is called nanotime, and it gives us a monotonic clock time, which is not affected by any other changes, but it's valid only within the single computer. So, can we use it? I think the key word here is this monotonic clock time. So as soon as we can have kind of a clock that is always ticking, we can try to synchronize the values. But before we start to reinvent the wheel, there's a question: can timestamps on my computers be synchronized? Because you probably heard, and I already said that, there is this NTP servers, so this like network time protocol. You can have a network server that is broadcasting, again, UDP, in most of the cases, and pushing the current timestamp to all the computers. NTP servers gives you a millisecond precision. So if you have more than 1,000 operations per second, that gets drifting, which is very dangerous. There's another protocol, which is called PTP, which is precision time protocol. And if you're crazy enough to invest in additional hardware, you can get sub-millisecond precision within your local network. So again, if you go for any geographic distribution, I haven't found a way to synchronize clocks because of latency, because of inability to broadcast some data, and so on and so forth. So I'd rather find a way not to do it. So what we can do and what we can try to use is we can use logical timestamp. Yesterday on Tomer's presentation, there was a funny thing that Tomer was showing the database rows, and there was a timestamp, and timestamp was 15, 30, 35, 40, and somebody laughed that It's just 40 seconds after 1st of January 1970. But that was a logical timestamp. That was just a value that was monotonically increasing over time. And plot twist, if you've been using Hibernate, there was this concept of a version in your Hibernate entity that was nothing else than a Lamport clock. So monotonically increasing version that let you reason whether the update you're trying to perform is based on the most recent data that is stored in the database. So the logical clocks. The implementation is that simple. If you read through Lamport's paper, which is just 6 pages, a lot of math trying to prove that things are working correctly. But ideally, what we are trying to do is we have a certain value to initialize the clock, and then with every operation, we just tick it and increase and increase and increase. And we use this clock as a version whenever we try to store something in our any repository. So whenever there is an update, the clock time is embedded in the data, and we can compare whether it's an older, whether it's a newer value, or whether we have some concurrency issue. We are able to order data. We are able to order data. We are able to reason that A happened before B. Can we stretch this idea to multiple servers? Because we have just a single value here, which is not really relevant if we have 3 or 5 or more nodes. Yes, we can. There is a concept of vector version. So we don't hold just a single value. We hold a whole tree structure where we have some identifier of a client or of a member of a node of whatever, and a monotonically increasing value, and monotonically increasing integer or whatever. And then within our versioned value, we have something and this vector clock. So whenever we have this operation where 2 nodes are trying to send messages with a version, we can try to reason if we are having a concurrent update. So we can have a version vector of node 1 of 2 and node 2 of 1, and the other is just 1 and 1. So we clearly know which one is greater than the other and what is the newer update. That's exactly what we wanted. On the other hand, we know that there was a concurrent update because node 2 increased the version and node 1 increased the version. So things happen concurrently. And I have to somehow reason about it. We can also have additional node, additional member participating and having a new update. So just the length of the vector is also important to us. It seems that we have something newer to manage. So as we figure out that we have this concurrent update, now there is a question what we can do about it. And I mentioned Hibernate. Hibernate doesn't really care. Hibernate just throws you an exception and say, hey, I tried updating that, that's not valid. That's a concurrent update exception, figure it out. You get a new value, you get your own value, you have to decide. And some of the distributed systems are also doing that. They are not storing a single value, they are storing a list of values, and if there is a concurrent update, they just throw it to you and expect a decision. One is better than another. But at least we moved from the second level of ignorance, that we didn't even know that there is a potential concurrency update, that there is a potential race condition, to a situation that we know that is happening and we can do something about it. So that gets us to the second topic. So do we have a data structure that can help us figure out and resolve these conflicts? There is a whole family of data structures, which are sets, maps, counters, that can be concurrently edited by multiple users and automatically resolve conflict in a sensible way. This is based, again, on a certain math. So kind of a precondition for having a conflict-free replicated data type is that we can merge those data types, whatever order of the data is coming. And we don't really care about potential duplicates coming from the replication layer. Once we have it, we are more flexible in building up or designing our store. So if you try Googling CRDTs, there are a couple of types that are out of the box. Funny enough, most of them are kind of append only or growing only, like growing only counters. If you would like to add and remove data, that's getting more tricky. If you look at the implementation of linked lists in Java, they kind of go in that direction of the conflict-free replicated data types. You can do similar things with a map. But why I'm talking about that? Because in our case, we might want to find a data structure that will help us resolve this particular conflict. So we have two nodes trying to do the same update and propagate that. So is there any data type that can help us? In fact, there is. It's very brutal, but sometimes it's helpful. So it's called the last right wins. So we try to converge at the cost of durability, meaning that if we have several concurrent updates to the same key, even though we successfully reported them to the client, we might only want the last one. And you might say, hey, that's just stupid, you will lose data. Yes, exactly, that's going to happen, and that's how many databases are actually working. Because in real life, all what I've covered is implemented. There's a database coming from LinkedIn called Voldemort. They're using version vectors and use timestamp to decide last right wins conflict resolution. They are leader-follower topology, so it's slightly easier to make this decision, but still, that's exactly what's underlying this database. If you have React is all-to-all topology. They're also using version vectors and also using LWW, conflict resolution. And finally, Cassandra is doing exactly the same. So before we get to a point of actually storing that data onto the disk, this is what needs to happen before we get there. So we've covered quite a lot. The cat is emotionally exhausted. So am I. I promise there will be cat pictures, so there is. If you would like to get more about that, I can't say it's a summary, but there is a very good book about designing data-intensive application. Unfortunately, it's like this thick, couple of chapters. Kleppmann is going into details of each and every algorithm, just showing you and trying to explain what are the consequences of one over another. Thank you very much. Hope you enjoyed that. I'll figure out this one. Yes. Yes, it is. Lamport clock is prone to race condition because it's supposed to be a single server. That's why an evolution of a Lamport clock by many is considered a vector version or a vector clock. But then vector clock has its deficiencies because as we store identifiers of all the servers, it can grow. So there is another paper about dotted version vector, which tries to address that problem. So as you get through that, you'll just, that's a rabbit hole. But essentially, yes, this is true. It's prone to the concurrent, to the race conditions. But it was like the first example of a logical clock. Any questions? If not, thank you very much.